Hello everyone. Today we'll be doing class 7 sound and we'll continue with what we have learned last time. First let's revise what we have been learning. So last time we introduced sound, how sound is produced. Sound is produced by the vibration of particles. And how does vibration happen? For example, if I'm hitting over here, what happens? Sound is produced because this stick vibrating, is it? So anytime there is vibration, when the particles vibrate, sound is produced. Then we learned about how particles move. So the particles move to and fro. And we discussed that sound travels in the form of wave. And before we actually have moved on with the movement of how the sound is transferred or how the sound is produced, we discussed about the types of wave. And how many types of waves are there? There are two types of wave. One is called transverse wave, the other is called longitudinal wave. Transverse wave, an example, ocean wave, the way it moves, the particles move up and down. Whereas in longitudinal wave, the particles move to and fro, like a swing. It moves to and fro. Okay, so I showed you an example last time. So this is your transverse wave. The particles move up and down, up and down. And longitudinal wave, the particles move like a swing. It moves to and fro. So the particles, they come closer, they move back, they come closer, move back. When they come closer, it's called compression. When they are in a normal position, it's called rarefaction. Okay. So I'm repeating, I'm saying it quickly because these are only revision, isn't it? Because we have done this in the last class. So how does transverse wave move? It moves up and down. So when it moves, it's called crest. When it moves down, it's called trough, isn't it? So it moves in a series of crest and troughs. It moves up and down. Okay, whereas longitudinal wave, it's like a spring. When you push it, when you push it from one end, they come closer, again they come back. The next particles, they come closer, again they come back to their normal position. So when they come closer, we call it compression. And when they come back to their normal position, it's called rarefaction. And the difference between transverse and longitudinal wave, we have completed till here in the last class. So transverse wave is a wave in which is a series of crests and troughs are formed. So transverse waves are the waves in which the particles move up and down. So how do the particles vibrate? They vibrate up and down. So they move like the ocean, the waves of the ocean. And longitudinal waves, the particles move to and fro. That means forward and backward. And thus they form a series of compression and rarefaction. Okay. An example here is given as seismic waves, sound waves. You can take an example of a swing, it goes, or you might have played a slinky. If you have played a slinky, you might have been knowing it. A long spring-like thing. So when you push it, when you push it in one end, what happens? A part of it comes closer and then comes back. So it continues, isn't it? So these are the differences between transverse wave and longitudinal wave. Okay, now we'll discuss how does sound travel. Okay, now how does sound travels? How does sound reaches our ear? For example, I am speaking right now, so you all can hear me because of the video. And the people who are around me can also hear my voice, isn't it? Now how do this sound transmit? How do this sound travel and reaches the ear of the other person? So this is what happens. See, say you are playing a drum over here. Now when you play a drum, the membrane of the drum vibrates, isn't it? So when it vibrates, what happens? The particles which are closer to it, the air particles which are closer nearby here, they also start vibrating. Okay, they also start vibrating. And then when they vibrate, they move to and fro. That means they move forward and backward. Now when they move forward and backward, say there is another particle. When it moves forward and backward, it touches this particle. Okay, this particle again starts moving to and fro. Now there will be another particle. When this particle was moving to and fro, it touched another particle. Now this particle will move to and fro. Okay, there will be another particle which it will touch, and then it will continue. So it continues to touch all the particles which are on the wave. So this is how sound will travel in a form of longitudinal wave. Okay, when the drum skin is struck, it vibrates, which causes the air beside the drum to vibrate. The compression and swishing of air particles creates a sound wave which is carried through the air to your ear. Now, I'll show you how the sound wave travels. Now, this is how the sound wave travels. Say, this is a tongue. Okay, these are called tongues, and these are made up of metals. Now, when you strike it, what happens? Starts vibrating. This tongues, they start vibrating. Now, when they vibrate, what happens is the particles which are near this tongue, okay, the air particles which are closer to it, they also get disturbed. That means they also start vibrating. Okay, they are touched by this, they start vibrating. Now, when they start vibrating, they will touch the particles which are here. They will vibrate, again touch the particle which is next, and then it continues. Okay, so what happens? A bunch of particles, they come closer and then they move. Once they are touched, they come back. Again, it pushes other particles closer. The particles again pushes another set of particles and then comes back. Okay, because they just move to and fro. They don't move from one place to another. They simply vibrate in their own place. So they come back to their normal position. So when they come together, okay, when the particles are pushed together, it's called compression. And when they come back to their normal position, when they are in a normal position, that's called rarefaction. Okay, so this is how longitudinal wave travels. This is how sound waves travel. That means to and fro. Okay. See, this is how it moves. This is actually how it moves. So the particles which are here, the speaker, when a person is speaking through the speaker, the particles vibrate and then they move closer. They come together, they get back to the normal position. They come closer, they get back to their normal position. So when they are closer, it's called compression. When they are in the normal position, it's called rarefaction. So this is how sound waves travel. And this type of wave is called longitudinal wave. Okay. So I hope you understood how sound travels. Sound travels when the particle starts vibrating. And how do they travel? They travel in the form of wave. Which wave? Longitudinal wave. Which means the particles, they come closer, then they move back to the normal position. Again, when they come closer, they push other particles. Again, the other set of particles, they are pushed together and it continues. Okay, and this is how sound reaches the ear of the person. Now, sound requires a medium to travel. That means sound travels through matter. Okay, now gases, liquids and solids. That means sound can travel through solids, sound can travel through water, sound can travel through gases. What is it filled with? The class here, if it's empty, it's filled with what we assume it to be filled with? Air. That's why the sound transmits to the different parts of the room. Okay, the person who is sitting nearby, they can hear the sound because the air particles transmits the sound from one particle to another, and this is how the sound reaches the ear of the person. The same way, we have some benches here, some desks here. So if I do this, and somebody places ear on this side, okay, when you lie here, and you can try it at home, just lie it flat on the table and then tap it from one end, or ask somebody else to tap it from one end. What will happen? You hear the sound. You close your ear, the air which is towards the ear, which is towards the air, just close it and then lie down like this. So when you lie down and just close one ear and then lie down on the table and ask somebody to tap it, you can still hear the sound. Or else you might have tried, I don't know if you have tried this or not, but you know, on a railway track, you must have heard, you must have seen people placing their ear on the railway track, isn't it? What are they trying to do? they are trying to hear the approach of the sound, approach of the train. That means sound of the train. Okay, because sound can travel in solid as well. So sound travels through solid also. And in fact, sound travels fastest in solids. Okay, then comparatively slower in liquids and slowest in gases because of the molecular arrangement. Now, see here, most of the sounds we hear travel through gases such as air. Right now, this is the example, isn't it? I'm speaking, people around me can hear because of the air present. And air is a gas. Some sounds that we hear travel through water also. So if you're inside the water, if you're under the water, and then if a blast happens, you can hear that sound. Okay, it's because sound can travel through water also. It can travel through any liquid also. Some sounds that we hear travel through solids. So, and I give you an example: people placing their ear on the railway track. Okay, sound waves travel slowly through the air. So this is the sound waves travel slowly through the air. Sound waves travel faster through water than air because the particles of water, that is liquid, they are closer compared to gases. That's why they can vibrate faster they can touch each other faster. Whereas this needs a lot of energy to touch each other, isn't it? Whereas for solids, since the particles are very much closer to each other, solid waves travels very fast, which means sound travels fastest in solids. Okay. For example, sound from a bell or horn. So we don't have to go through these examples. We'll be discussing the sonar later when we'll be doing the sound only, the later part now. So just understand these differences. That sound requires a medium to travel. It travels through solids, liquids and gases. And sound travels fastest in gases, slower in liquids and slowest in gases because of their molecular arrangement. So see, this is how it happens. Gas fast, liquids faster and solids fastest because of their molecular arrangement. So how sound travels? The speed at which sound travels from one place to another depends upon the medium. How closely the packed molecules are in matter. So if the molecules are compact, that means tightly packed, the sound will travel faster. And then liquid and then gases because of their molecular arrangement, as I told you. Now, I've been mentioning it that sound requires a medium to travel. That means in vacuum, sound cannot travel. You cannot hear anything in vacuum. If there is no air, no medium, no liquid, no solids, then you will not be able to hear the sound. This is what happens in space, isn't it? No atmosphere, no air, you cannot, no matter how much you scream out there, no one will be able to hear your voice because there is no medium. Okay, now an experiment to prove that sound requires a medium to travel. This is called a bell jar. Okay, bell jar. You have a bell over here, electric bell. Now there is a vacuum pump over here. There is an electric bell and this electric bell has a cork. It's completely shut. That means no air can enter it. Now all the air which is inside this electric bell, bell jar. Okay, all the air which is inside this bell jar is removed. Okay, and then it is sealed. Once the air is removed, it's sealed. Now what will happen? If there is no air present inside the jar, nothing, no medium, except the bell is here. You will not be able to hear, there will be no air present here. Now you ring it, okay, you push the button, you will see it vibrating, you will see the electric bell vibrating, but you will not be able to hear the sound. Okay, what does it prove? It proves that sound requires a medium to travel. Now if you just open this cork, what will happen? Air will enter it. Now close this, seal it, and then ring the bell. What will happen? You will hear the electric bell. You will hear the bell ring. What does it prove? It proves that that we have air here and we have a medium here for the sound to travel. So it's very important for a medium to be present for the transmission of sound. If there is no medium, no solid, no liquid, no gases, sound will not be able to travel. Okay. How do astronauts communicate in space? As we know, there is no air, there is no atmosphere, there is no air, so there is no medium in order to communicate. You can shout over there, you can scream at the top of your voice, but still the other person will not be able to hear your voice unless we use radios. Okay, so this is what they use to communicate over there in space. So you must have seen that, isn't it? They use this. Now see here. Because there is nothing out in space like an atmosphere, the sound waves from one astronaut's whistling can't travel over to the other astronaut's ear. That means whistling, talking, nothing can be heard. Unless, what do they use? That's why the astronauts use radios. You saw the radio, isn't it? Sorry. You saw the radio? Unless they use the radios to communicate, even if they are floating in space right next to each other. Okay, so because this radio, they produces some electromagnetic waves which converts, because of the electromagnetic waves, the sound waves get a medium so they can travel. And thus they use these radios to communicate with each other. If there is no radio, they will not be able to communicate with each other. However, they can. This is when they are out on the space, when they are outside space. But when they are in the station, okay, when they are in a space station, they can talk. Now, when astronauts are inside the International Space Station, they are in a simulated atmosphere. It allows them to breathe without wearing space. So you might have seen it, isn't it? Those who are inside the space, the International Space System, the station, they take out their mask and they can talk without the suits. Inside the space station, sound waves travel like they do on Earth, and astronauts can whistle back and forth as much as they like because it's made in such a way that it's filled with air, in fact. Because they can breathe, okay, they can breathe in oxygen and all, so it's become easier for them to, it's like, being on Earth only. So they can take off their spacesuit and they can communicate, they can talk like they are at home. But when they are out on the space, then they need to wear the suits and need to have radios in order to communicate. Now, these are the chart to show the speed of the sound. So the speed of the sound in dry air is at 332 meters per second. So generally when we talk about the speed of the sound, we take it to be 332 meters per second. Hydrogen 1284, that means it's a gas. So water 1498. Glass, it's 5170. Iron, it's 5130. So what is happening? Air is a gas. So the speed is less, which is 332 meters per second. Okay, that means in 1 second, how much distance can the sound travel? 332 meters. Whereas when we compare it with glass, it's very much higher compared to gas. So what does this prove? This proves that sound travels fastest in solids. Since glass is a solid, it travels fastest in solid compared to gases. Okay, now light is faster than sound. Light travels faster than sound, and that is one reason why we see during the before the rainfall, sometimes when there is lightning and thundering, we see the flash of the light, isn't the lightning, we see the flash, and then after some time we hear the thunder. It is because light travels much faster than sound. Okay, light travels much faster than sound. So in fact, much faster than sound. Sound is a mechanical disturbance that requires medium to travel. So sound requires medium to travel. Light does not require a medium to travel. You know the rays of the sun. Sun is miles and miles away from the earth, isn't it? And despite that, it reaches the earth in no time. And there is no medium also. So despite not being any medium out there, light reaches the earth in no time. Which means light travels faster than sound. Light doesn't require any medium to travel. Sound requires a medium to travel. Sound always needs a medium to travel, unlike light. So as I told you, we see the lightning first before we hear thunder, because light travels faster than sound. Okay, so we'll stop till here. In the next class, we'll continue with the sound only. Till then, have a good day and enjoy it.